Welcome to video 2 in this pre-matriculation lesson, sort of demonstrating some of the things we want you guys to carry knowledge into the curriculum. And we're covering the way that the heart works in detail, to a lesser extent how the systemic circulation works. And in this video we'll cover a little bit about the lungs, and we'll see how some of that translates to lung function. So first of all, we ended the last video talking about the heart and how it functions. You should know that the heart is actually two pumps. A right heart, which pumps blood into the pulmonary artery and into the lungs, and it perfuses the pulmonary circulation. And the left heart, which receives the blood from the pulmonary circulation and then pumps it into the systemic circulation. And we say that the right and the left heart and the lungs are all in series. Each one receives all the blood flow from the one preceding it. So the right heart is in series with the lungs because the output here, normally 5 liters per minute, all goes into the lungs, and then all of that output leaves the lungs and enters the left ventricle. So we say that the lungs are in series with the right and left ventricle, and the left ventricle is in series with the right ventricle. All of them in a row, each receiving all the flow from the previous one. Okay? In contrast, when the blood exits the left heart, it enters the systemic circulation. Okay? The systemic circulation isn't just like one organ, it's all the other organs in the body. And so what happens is each of these organs receives some of the cardiac output. The cardiac output is split from here, and the flow through the liver is part of the cardiac output. At the same time, the kidneys get part of the cardiac output. All these systems get part of that 5 liters per minute. And because that 5 liters per minute is broken up into parallel circulations, we say that these beds are in parallel with each other, okay? You will note the arterial pressure in the aorta, which is generated in order to perfuse all these organs. So blood flows from high pressure to low pressure. Your heart, its function is really to generate pressure in the aorta and in these arteries. And if you can maintain high pressure in the arteries, blood will flow across the system from high pressure to low pressure into the veins through each of these beds. Okay? So the heart generates a pressure of about 120 millimeters of mercury at peak systole, and it has a pressure of in the aorta, and the aorta has a pressure of about 80 millimeters of mercury at the lowest point during diastole, roughly. You guys know that varies, okay? And that pressure is used to perfuse these organs, okay? All right. The pulmonary circulation, unlike the systemic circulation, this, as I said, is in series with the right heart. And basically this output from the right heart perfuses the gas exchange areas of the lungs, okay? So the purpose of the blood is deoxygenated here in the pulmonary artery, and the pulmonary vein, it exits the lungs and it's oxygenated, okay? The walls of this system are what we call compliant. The concept of compliance is a really important one in physiology, and what it is a substance is more compliant when it stretches. So if you're talking about a tube like the pulmonary artery, if you increase the pressure, if the walls stretch easily, then we say that the walls are compliant. If they don't stretch as easily, then they're less compliant, okay? So if we look at the pressures in the pulmonary artery, we remember in the aorta, the peak pressure during systole was 120 millimeters of mercury. Look, it's about 20 to 25 here. So it's much, much less. It's about 1/5 of the pressure in the aorta. And the pressure during diastole, once again, much lower than that 80 millimeters of mercury that we saw in the aorta. Well, each one of these is receiving 5 liters of blood per minute. So why is one 120 millimeters of mercury at peak systole and the other one only about 25? A good part of the reason for that is the fact that the walls of the pulmonary artery are more compliant than the walls of the aorta. They stretch easily, so they hold a higher volume at a lower pressure, or in this case, the same volume at a lower pressure. Okay? So that's the concept of compliance, all right? And this will come up over and over again in physiology throughout the course of the next 2 years. So, since we're talking about the pulmonary circulation, let's talk a little bit about how the lungs work. This could turn out to be important in the host defense block, where Dr. Richards will be assaulting you with a variety of different microbes in somewhat great detail, some of which may cause pneumonia. And we'll talk about the effects of pneumonia in very, very general terms in a second. So let's talk about how respiration works. Let's start with inspiration. Inspiration is initiated when you contract your diaphragm. So this is the diaphragm here. See this dotted line? When the diaphragm contracts and the muscle fibers in the diaphragm shorten, the diaphragm moves from here to where the dotted line is. When that happens, you expand the volume of your chest cavity and you drop the pressure in the chest cavity. It's like pulling out, and the pressure drops when the volume expands, okay? Well, when that pressure drops, it drops below atmospheric pressure, which is the pressure at your mouth. So as your chest expands and the pressure drops, you've got low pressure in your lungs, relatively high pressure at the entrance of your mouth, atmospheric pressure. Air flows just like blood, from high pressure to low pressure, and it fills the lungs as it does so, okay? So we have a common concept. Blood, fluids flow from high pressure to low pressure. Air does the same thing. It flows from high pressure to low pressure as you inspire and bring air into your lungs, okay? Air fills the lungs, the gases move into the alveoli, which are the gas exchange units of the lung, and oxygen then diffuses into the blood, and carbon dioxide diffuses from the blood into the alveoli. After that, you expire, and during expiration, you relax the diaphragm. So the diaphragm's contracted here, I relax it, the muscle lengthens, and as it lengthens, the diaphragm pushes into the chest cavity. And as it pushes into the chest cavity, it takes the air that's in the lungs and it compresses it, and it increases the pressure. So now we've got high pressure in the lungs. The pressure in the lungs exceeds atmospheric pressure, which is the pressure at your mouth, and you expire. And air moves from high pressure to low pressure out into the atmosphere, and you expire what you took in, okay, with different composition, more carbon dioxide, less oxygen, okay. All right, so that's how the lungs work. In very many ways, the same as the heart. Blood and air move high pressure to low pressure. All right, let's take a look at the alveolus. This is an alveolus. It's surrounded by capillaries, okay? And the first thing that you should notice is how thin the barrier of exchange is. It's basically a single layer of cells. The alveoli are a single layer of cells with a basement membrane, basically, and the capillary at this level pretty much the same thing. It's so thin. This isn't a red blood cell. See the indentation there? That's the indentation within the blood cell. You can actually see that through the membrane here, through the capillary and through the membrane of the alveolus, which is this empty space here. So this is how thin that membrane is, and the reason it's so thin is because you have to keep the barrier for gas exchange very, very low. And the reason is because you need to decrease and keep the distance of diffusion short. Diffusion is the process by which a substance moves from high concentration to low concentration. In this case, the substance is moving from the alveolus into the capillary, if we're talking about oxygen. And when substances move by diffusion, they're going to move most efficiently over short distances. Distances of diffusion must be kept short. Diffusion is not very efficient when those distances are long. The reason is because diffusion doesn't work the way that anyone with common sense might assume that it works. You're a medical student now, you're not allowed to use common sense too much. You have to be able to take the concepts and understand the way the real world works. So if I have a substance S and I say it moves 1 micron in 5 milliseconds, and then I said, okay, how long will it take for S to move 10 microns, which is 10 times farther? Well, a person with common sense would say, well, it took 5 microns to move 1, it'll take 50 to move 10. And that person would be wrong. It doesn't take 50 to move 10. In fact, the time of diffusion varies with the square of the distance. And what that means is that if you're talking about 5 to move 1, if you're moving 10 times farther, 10 microns, it will take not 10 times longer, but 10 squared times longer, or 100 times longer, which means 5 milliseconds to move 1 micron. If you go 10 microns, it will take 500 milliseconds. So over 10 microns, not nearly as efficient as it is over 1 micron. So distances of diffusion have to be kept short. And what you will find is that over and over again, as you go through the way that these systems work, the systems work very hard to keep distances of diffusion low. Your capillary membranes are thin so that nutrients can get across the capillary wall into the tissues easily. Your alveolar walls are thin so that oxygen can get from the alveolus into the blood easily. Okay? Things like that happen over and over again as you go through the systems, and this is the reason why that is the case. Okay? So, if we talk about pneumonia, we're talking about a process by which your lungs become inflamed due to the invasion of some microbe that it's Dr. Richard's problem to teach you, not mine, thank goodness. Evil enough for another day. The bottom line is you get this inflammatory response, and what happens is the membranes in the lung thicken and they accumulate water, and you can actually accumulate water in the alveoli. Okay, so what does that do? Well, if I've got these big thickened membranes in my lungs are becoming heavier. And more important than that, the walls of the alveoli and the walls of the tissues of the lungs are becoming thicker. And another way of saying that is that they become less compliant. And if they become less compliant, more difficult to stretch, that means during inspiration, it's harder to inspire, okay? And so decreased compliance of the lungs makes it tougher to increase lung volumes. And that can cause respiratory difficulty. So you get what's called a restrictive lung disease, which is what pneumonia is, okay? It restricts your ability to inspire because the compliance of the lungs, the stretchability of the walls, the pressure needed to increase the volume increases, so the lungs are less compliant when that is the case, okay? All right. We also have that increased alveolar wall thickness. That means we've increased the distance of diffusion, which means it's going to be a lot tougher for oxygen to get from the alveoli into the capillaries because it has to go through the water in the alveoli, it has to go through the thickened edematous membranes. And so when you increase the distance of diffusion, you decrease the efficiency with which that happens. You're having trouble getting oxygen into your capillaries, your blood's not as oxygenated, bad things happen when that happens, right? So pneumonia, not a great thing, but it's a very good demonstration of a couple of very interesting general physiological concepts that tend to recur over and over again as you go from organ system to organ system. All right, that's all I've got for this video. Thank you for your attention, and we'll move on to the third video.